Works. One moment, I will put it in a learning system. Maybe sometimes will be interested in this.
I got the two values. How I can use that?
What?
I'm sorry.
I don't understand the problem.
Okay. In this sum, in this area, minus 3, J133, and the 3, 4, the fourth one is here.
Yeah. So, what's the problem?
This value J2 is 2 multiplied by this
yeah,
value.
so is it problem to write 2 multiplied by complex of?
This I need to, no, it's a multiply by complex. But the fourth one, I got
as I
two
told,
power
then this is Excel. Yeah?
Yes.
But we speak on what? On CLAB.
In
okay. CLAB, when you fill array, you open
the
bracket. At a position 4, you will write J2 minus J1.
Oh, J2 minus J1. Because the direction is that same direction. If the opposite direction means J2 plus J.
In opposite, yeah, but in this case.
Okay, I understand now. But I need to multiply by simple way minus 1.
What's the problem? You write J2 equals
J2,
2 multiplied by complex and what it's in.
Okay. Thank you.
It is easy. But I need this in my learning system. I need to add my lecture to a learning system or no one will be okay. Someone may miss it. Yes, solution. I don't need this. I can free this. This is also. Yeah. Time to do something. Time to do something. I prepared something for today. It's quite interesting. It's answer to the question, what shall I do? What should I do if I need to calculate not DC and not ideal AC circuit? For example, I need to calculate rectifiers, circuit power from rectifier. Is it possible? It is possible. So how can I calculate? Circuit power from rectifier. Here I have model. 3-phase transformer. Nice 6 diodes rectifier full bridge and circuit powered from it. transformer, Fourier, normal transformer. I can even power it. And let's say
But the output will be greater than
normal, typical.
okay.
Where's that voltage? Here is voltage it produces. It's not AC.
It's a DC, pulsated DC.
It's not AC and it's not pure DC current. Yeah, it's something.
Pulsated DC.
What should I do? How can I calculate such network? It's a bit complex task, isn't it? Not so easy. So, what do we have? What do we know? Previously, I have shown DC circuits. Yeah, I started from DC circuit. And ideal AC circuit. Yeah, yeah. But this one is not neither DC, neither AC. It's a complex circuit. Some kind of complex current circuit. I don't have direct tools for complex currents. I have only ideas for DC and AC. So, I will use what I have. I will apply a Fourier decomposition. There is one of the core ideas of modern, let's say, engineer math is a Fourier transform. Jean-Baptiste Fourier offered an idea. If you have some physical signal, what can be treated as a periodic. So it repeats. Here, P capital is a period, repetition period. It's greater than 0 and less than infinity. And n is an integer. Minus infinity, minus 1, 0, 1, so on to infinity. It can be anything with a repetition period P capital. It should be periodic. In our case, we have an AC, for example, we have an AC voltage. AC voltage repeats with a frequency 50 Hertz here, meaning what we have period 20 milliseconds. So, Fourier idea. I can substitute any periodic signal in a way this is DC component plus some, like here I can 1 to infinity cosine plus st sine divided. This is key idea of Fourier. I can substitute, I can rewrite it, 1 second, I will rewrite it in bit compact form, but this is key idea of Fourier. What any complex voltage, current, anything, but periodic, it should repeat itself, can be substituted with, let's say, DC component and a set of ideal AC components. can be equal again C0 divided plus with 1 to infinity A cosine K omega t. Here is a Pythagoras theorem plus sk squared, and omega is nothing else than double p divided by repetition period. Time. Very nice idea. You can see that each this component is an ideal AC voltage or current. Sine or cosine, there is a little change, it's only 90 degrees. How can I get? I need these two. Not two, I need many of them. I need a set of Fourier factors of Fourier coefficients, which characterize my signal. They will give me ideal component. I can solve network for DC, I can solve network for AC. Idea is to decompose real complex voltage into set of ideal components. So K can be found as divided by X from 0. My signal, it can be voltage, and can be current, it can be anything. Cosine and sine factor. This is for cosines, this is for sine. 0 to sine of K double P divided by P multiplied by time. Here are formulas for Fourier coefficients, to obtain this Fourier coefficients.
Professor, it's make full wave or half wave?
It's
Any. Okay.
This one full.
This one is full.
It's three phase. It's better. It has. It will have 6 waves, not 2.
Ah, okay.
6. It's three phase. But don't worry, we can take anyone. I'll show how to. Oh, views appear and disappear. Okay, let's see what next. These nice formulas, but I don't want to calculate them by hand. I want to do it numerical. I will do it numerically. To do so, I need one nice idea. Let's say I have some periodic signal. To get first cosine factor. So C1 will be from 0 to time cosine to get C1 I need to calculate this. It's a first cosine. I don't know how it works. Maybe something like this. Cosine multiplied by this S naught t. Maybe something like this. What the physical meaning of this integral.
Which,
Area.
comes just periodically, continuously.
Yeah, but here. Here is my period. It's enough. What's the physical meaning of this? Area of the white figure. I need area of this figure. Let's take because a look. If I do it numerical, what will I have? Continuous signal? No, table of values. My signal will be represented as a table of values and multiplied by cosine, it still remains a table of values or discrete time signal. This nice set of dots starting, let's say we have for one period, we have 1, 2, 3 n dots, n measurements, n values, n elements of array. Between them, spacing tau is period divided by number of values we know. Let's say they are equal. In the memory of our computer, we will have table of values, and table of values represents signal not as a continuous signal, not a continuous voltage, not a continuous current, but as an object in space of discrete time. Because no one bothers to calculate between nodes. We know only in nodes at measurement points. It's what we will get for example, from analog to DC conversion. Nothing is known between samples. Well, maybe it was no signal at that time. No one knows and no one will. So, returning to, I need this integral. It's an area. It's an area of white figure. But I can approximately substitute it. Simple drawing such rectangles. Area of one such, it's pillar, not pillar, or area of such one rectangle will be, if it has a number I, let's say. So area of it will be signal value at time I tau multiplied by cosine of, case one moment, I minus 1. Why I minus 1? Angle here for cosine is 0, but number of point is 1. That's because it will be I minus 1 by double P divided by number of measurements. Yeah? I have totally n such rectangles. For one rectangle, angle will be double P, full circle, divided by number of such rectangles. And multiplied by width of such rectangle by 1 tau. So, I can rewrite this C1 as, and if I count all these nice rectangles together, I will get area disappear. Sum where I changes from 1 to number of measurements. Signal value at the point I tau. Cos I minus 1 double P divided by number of measurements. And it is it. That's the way I can get cosine factor for base frequency. For any frequency, it's easy. If at a base frequency we have double P rotation, for double frequency we will have 4P, for triple 6P, and so on.
Professor, in case the term of full wave means how we can calculate it?
Be patient.
Full wave.
Full wave, free wave, C wave, anything, it just should be periodic. We patent, I'll show. And now you need to understand how I will solve it. So, for any, it will be 2 divided by n. Sum that I starts from 1 and ends by number of measurements per period. Value from signal table, cosine I minus 1 double P divided by period. Absolutely in same manner I can get factors for sine equals to 1 I tau sine I minus 1 double P divided by period. These two nice terms define basis for discrete time Fourier transform. It allows me to convert table of signal into ideal sine and into ideal DC component C0 and set of ideal AC component CK. I should, if I want to use electrotechnics theory, I need to take a minus here because cosine. It's because of being at 1 omega for number 1, double for double frequency, triple frequency, and so on. They will be at a kind of progression. Base frequency, double frequency, triple, quadruple, and so on. Ideal currents. Now, what can I do? Let's say I have something signal. I need to calculate table of values. I need nice table where k is time, I from 1 to n. Time should end at period, and here should be values, values, values. Involves I need to create a table of values. Table of values is an input for discrete time Fourier transform. When I perform Fourier transform, results will be DC and 1s1, C2, S2, and so on. I can add, it's one moment, Nyquist frequency. there is a Nyquist theorem telling what frequency of sample should be at least twice as the higher frequency of signal. This means what I can calculate starting from DC and first second minus 1. This is the last stop. If I try to calculate more, I will receive nonsense. I will receive. So I can get table of ideal currents. Now I should do network solution job. I need to calculate my network regime. I prefer to use nodal voltage equation. So I need to solve a nodal voltage equation. This is my general form of nodal voltage equation. I will not use current sources, and I will do the trick. Here I will put C, and it will be general C means S for each frequency. Since I decompose my signal into set of n-1 AC plus 1 DC, I will need to perform calculus for each, not a period, each frequency. For each frequency. So I will need this also. I will take a zero-based node. I will need to perform calculus n-1 times for AC plus one more for DC. Here branch nodes, resistance, transposed branch nodes, resistance for each frequency, moment, important moment. Each frequency will have its own resistance matrix. So for active resistance it will remain F. For coils, J, K, omega A. Because if you double frequency, impedance will double, it triple, so on. For capacitors, will be 1 J, K, omega C. For each frequency, for double frequency, capacitor drops twice. For triple, 1/3, and so on. And for mutual inductance, it will be J, K, omega element. This will go symmetrically in resistance matrix. Clear? I'm repeating our AC calculus what we made, but multiple times for multiple frequencies. I will get nodal voltage and branch currents in a form of Fourier coefficients, Fourier factors. So for each voltage, I will, in general, I will have kind of voltage matrix where this will be nodes. At the first dimension, it will be nodes. Voltage at the first node, voltage at the second, voltage at the number of nodes position. And here will be number of harmonic, or actually a multiplier of base frequency. 1, 2, up to -1. It's a kind of matrix. Each row of this matrix can be converted into real voltage via inverse Fourier transform. So I also need DC, and it will be 0 plus sum of real of voltage cosine k omega plus minus imaginary part of voltage sine omega t. Same with current. With Fourier synthesis, we will get real time function. This, in theory, this allows us to solve stable regime, not transient, but stable regime of any linear network. The network should be linear because we assume superposition theorem is enforced. And what I need to say, and it should be periodic. This let's say technique is applicable for periodic voltages and currents and so on. Okay, let's see it in reality. How it can be done. I have a quite complex network. What connection I have? It's start. Okay. Start belt. Ground. This is not grounded. I've chosen full bridge. Here is my full bridge. A, B, C phase. This will be base node, just for my convenience. Full bridge. Let's start with speed. Base line. One, two, three, four, five, six. All here.
I need to see the output again. It's lagging. Lagging or
Okay. It should be 1, 2, 3,
It's
4, 5, 6. Count. Period is 20 milliseconds. Here, scale, wait 1, 2, 4, here 10 milliseconds. Maybe I put on a large screen. Try to get it on a large screen. Here comes my signal. I hope it's visible. Yeah, it can be seen.
it's a one full resolution.
One full is 6. To make it easy, I can disconnect one phase.
Ah, okay. Okay.
Some familiar, more familiar, let's say.
Yeah. Okay. So 1,
Yeah, it's 1,
2, 3. Okay.
It's 4.
Wow, it's nice.
It's for full bridge.
Full bridge, yes.
So, what should I do? I should show how to make a
Sir, it's star connection.
transformer. Yes, start. Should help. No. Okay, it's not.
Star connection.
Nice voltage. That's the way. Make it. DC mode.
Simply, I can connect the capacitor to the panel.
You can cut. Capacitor is waiting.
Right.
At the first, I need table of pure signal. Which phase to disconnect? K is without one phase. How can I do it? I need a table of signal. I need a table of signal. One moment, I will share Syllab screen. let's say clear. I will put something here, but first, how many dots should I have? For example, I will take with a step of half degree. I need to fill a table of signal. For this nice EMF, I need an EMF, and what EMF? EMF of I don't know what's now here, but I can measure. It's 1175. 1175. One equals to 11.75 volts. It's a phase voltage. How can I get this one? I have bridge rectifier powered from linear voltage. What will be mass for it? Simple absolute value of voltage, isn't it? So, equals to 1 up to n. Yeah. Equals to multiplied by P, double P, divided by n, and multiplied by I minus 1. It's a value of omega in radians. Value of signal at I should be line voltage is 1 multiplied by S squared and 3. Yes, should be line voltage multiplied by sine of but I have a rectified. Let's check, do I calculate signal let's see what happens. Something familiar, isn't it? Look. Is it close to signal we see on the scope? BTV, let's check. Amplitude of my signal is measured 28 volts. 28 volts measured here. Sorry. Bit smaller. Why? Why? Oh yeah. Oh yeah. Oh, it's a multiplied by SQRT of 2. I measure it with voltmeter, but voltmeter shows me effective value. I need now it should be 28. Yeah? Stupid mistake, isn't it? Okay, I have a table of signal. One moment. I'll show it to. One moment. I will run chart and you missed everything. What the? Oh, here you can see, those who viewing my screen, you can see a chart very close to the one we see on a scope. Okay, let's go forward. Let's go forward. And what we will go forward, I will left this. Now I need to perform. Ah, 1 second, full bridge. This one is 4 diodes. I need a full bridge. With the full bridge, it will be a bit difficult. For simple rectifier, it's just an absolute value of sine omega line multiplier. For the free phase, we will have 6 waves, and it can be written as U line multiplied by maximum value of sine omega, sine of omega minus 2/3 pi, and sine of omega plus 2/3. Maximum of absolute values. I can do it like this. Equals to max array of epsilon sine of one bracket, 2 brackets, 3 brackets. Minus multiplied by and divided by 3. Here is it correct? And the same here should be plus. And max, to be correct, I need to do like this. So this should be excluded. Let's see what I got. I will got an error. No. 1, 2, 3, 4, 5, 6. 6 of them. But I think I can write it in a bit different way. I can write it in a bit different way. Absolute of here will be 1, 2. I will write it a bit just to save space. This okay, square okay, this one okay, and this one okay. And this should be also multiplied by E. Let's check. What we got, 28.5. And what will we see in reality? What will we get? Please. 28, it runs around 28. Good. One second, I will show chart to online viewers. Here is, for those who look online, here is chart of the voltage. So, this is my rectifier. Single phase or three phase, easy, easy. Now more complex task. I need to perform a discrete time Fourier transform on my signal. Now, DFT. No. Oh. I will reuse. 1 second, I will fix it. Okay. I don't need to calculate actually all harmonics. In theory, I can calculate how many? 790. But it's actually it's useless. So I will limit my row up to 70 components. Here should change this is my signal. Sine, cosine, here everything fine. So, what I got here? I need to calculate these two sums I showed. Here, the part calculating sum for cosine, sum for sine, and ck, sk. This piece calculates DC component. I need to check my work. How can I do it? I can perform an inverse Fourier transform and compare to my signal. If synthesis from Fourier components yields the same signal what I put in, if I will see the same rectifier output, I perform conversion correctly. So I will create a plot with original signal and result of synthesis. Here, this part perform a synthesis backward from the C and E factors I've acquired with discrete time Fourier transform. This will allow me to check line 27. Where is my line? Wait. Sorry. Oh, my figure that I got. 139. This should be S, and this should be S. Oh, what I got. Take a look what I got. Plus line synthesis, green line original. Here is very interesting moment. Green line original and line with plus mark synthesis. See how similar they are? So, can we tell what I correctly perform a Fourier transform? No, we can recheck it. How can we recheck? Where is my program? Let's return this is not good. Nice. Very close. Something 0.2 volts here at the top. Very close. Good. So I can I can tell now what I have a Fourier factor, set of Fourier factors, or Fourier coefficients representing my signal, my voltage. What will be the next step? Circuit. I need to solve my circuit. And to solve my circuit, at first I need to draw it. Let's go for circuit. Go for circuit. What I got in my circuit. From the rectifier it goes to coil. I will show it as a resistance, and coil is 100 millihenry and its series resistance is 20.3 ohms. It's a real coil, so 20.3 ohms. Here I have a capacitor, 1 microfarad. Oh, then 1. Okay, we'll switch to 1. There's 1. There should be 1. Next element is very complex. It's a standard metal inductance. So it has resistance, own inductance, and where is my okay, primary side is 17.5 ohms, own inductance 82.77 millihenry. I have also added 200 ohm resistance in series, and coupling is 100 millihenries. This is grounded here at secondary side. Ohm are 35.9 9 ohms and 204.5 millihenries. In all it's loaded with 600 ohm resistance. Here is my circuit. It's a complex circuit with metal inductance. Not everyone will try to solve it. What should I do now? I need to mark nodes and branches. Let's say this will be node 1 and whole rectifier will be branch 1. Capacitor, let's say it's a branch 2. Here this resistance is needed. I can connect scope here to see voltage. So this will be node 2, and this one will be branch 3, and this, let's say, branch 4. Here will be node 3 and branch 5 and 6. Looks nice? This is this coil, this capacitor, and this nice mutual inductance. It's a set. Это, how to say, guaranteed 100 millihenries of mutual inductance. 200 ohm resistance and 600 ohms load. What will be the next step?
We need to construct EM matrix.
Yeah, we need to represent network as a M matrix. 1, 2, 3. 3 nodes and 1, 2, 3, 4, 5, and 6 branch. This will be for number 1. Okay. Number 1 inflows in first -1, 0, 0. Number 2 flows from so here will be 1, 0, 0. Branch 3 outflows from 1, inflows in 2. Branch 4 outflows from 1 and goes into base, so nothing here. Number 5, this is ground, so from ground to number 3. One remark, I can solve only network represented by connected graph. So, in theory, this part is separate. I can put an earth point here. If not, we should create this ring artificial. We should add large resistance. Anyway, in reality, there will be insulation resistance and capacitance against ground. So, it is not possible to solve interrupted network or not connected. Okay, from 3 to ground. Here is my first incidence matrix. I need to fill it. So equals to -1, 1, 1, 0, 0, 0. This one 0, 0, 0, y0 -1, 1 and 2 zeros and 4 zeros 0, 0, 0, 0 -1 and 1. Is it clear how I fill this matrix? It's very simple. Node, branch. If branch inflows in node, we write -1. If runs from node, we write 1. Very simple. I got the incidence matrix. Next step. Next step, I will need to repeat calculus as many times as I have AC component. So it will be cycle for k from 1 to number of harmonics. And what will I do inside it? First, I will have an EMF vector. A should be. I have only one source in the first branch, and it's C from K. It should be complex. Complex of C from K minus X from K. It's for the first branch. And 5 zeros. 1, 2, 3, 4, 5. EMF, it's an AC component I got through Fourier transform. Next, resistance. Let's write first branch resistance. First, maybe it's, let's define frequency, should be, let's say, 50 Hertz, yeah? And before I do this, I will define as K multiplied by frequency multiplied by 2 and multiplied by P. It's a K omega. Clear? Omega double P F and number of harmonic. 1 for base, 2 for double, and so on. So here I will you know, this way, if this way I will need to put a complex and 0. Now it will be J omega. Why J omega? I will simplify my life. For the first branch I will write 20.3 plus J omega multiplied by 100 minus 3 because it's millihenry, and I got 20 real ohms plus J omega A. For the second branch, 1 microfarad, 1 divided multiplied by 1 A minus 6. 1 microfarad. What's the third range? It will be 17.5 plus 82.77 A minus 3 and third branch. Okay. Number 4, 200 ohms, simply 200. Number 5, 45.9 plus J omega multiplied by 234.5 A minus 3 because it's in millihenry, and Last one is 600 ohms. Very nice, but that's not all. I have created, this one is a main diagonal of the resistance matrix. My resistance, I took the most complex thing with the metal inductance. Metal inductance produces non-diagonal elements in resistance matrix. That's why I will do now. I need to put metal inductance. It's between branch 3 and 5. You see?
Yes.
So elements 3, 5 and 5, 3 equals 5.3, 3 equals, and what it equals? Multiplied by 100 minus 3, because I have 100 millihenries of metal inductance. I have put my metal inductance in resistance matrix. Now what I will need? Inversion. I need inversion of resistance matrix. How will I do it? I will use my Jordan function. Jordan inverts it's a simple inversion function. So 1 equals to Jordan function. It's a Jordan-Gauss technique of matrix inversion. I got inverted. I have MF. So now I can do what? I can compose nodal admittance matrix will be transposition. I forgot one thing. I need transpose. 1 second. Do I? This is 1 second. I will. Yeah. I need this one. I need a transpose of M matrix. M multiplied by Z1 and multiplied by M transpose. I have nodal admittance matrix. Also, B vector will be M multiplied by Z1 and multiplied by E. Yes. Why? M Z inverse E. Now I need to, what I got? I got a system of linear iteration. I need voltage. But I need to solve the system. I will copy my Zeidel function. Yeah? I have a Zeidel function to solve system of linear equation. I will put it in here. Yeah. And now here voltage voltage, first dimension K, equals to solver of y and b. I will get, for each k, I will get one column of voltages. Also, I'll need currents. I will need currents, very simple. Looks okay. Wait, let's check for errors. Syntax error, unexpected identifier. Expecting and. Wait a second. Where is my? Oh yeah. No. Okay. I don't know what is MS. Don't know what is MS. Yeah, I know why, because when I used transpose, I forgot to I forgot to do this. I forgot to measure my okay, something happened. Now question, what is okay, show me absolute of. Let's take a look what we got. Oh, we got not a number. 100 hertz, 200. Oops, not a number. I'm not very happy. Not a number. Something good. I see not a numbers. No, not a numbers, not a numbers. I'm unhappy with not a number. Looks nice, but in this case. Here everything fine. 1, 2 should arrive at 6. Yeah. Oops, not a number. Where is my resistance? And with 10. Solution, not a numbers. One step. 1, 2, 3. Not a number. unhappy. I'm a bit unhappy with not enough. Это 12 pound. Oops. Not a number, not a number. Sometimes this helps. No, 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 no. Everything fine. This is fine, this is fine, this is fine. This is fine. And for this version, this is fine. No need to panic, this is fine. No, 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 everything fine. I see nice. I see nice voltages. We can take it, we can take it, we can take it. Okay, let it be as it be. I put a gauss. I got voltages, I got currents. Now I need to perform a what? I need to perform synthesis. I need to create. Sorry, 1 second. 1 second. One tiny problem. I forgot to calculate DC regime. I have calculated 70 AC, but I did not calculate the DC regime. In ideal, I need to create a separate scheme for DC regime because I need to remove coils and I need to remove capacitors. Because for coils, it will be, for ideal coil, its resistance is 0, and for ideal capacitor, it's infinite in DC mode. But I will not do it. I will go a bit brutal way. I will calculate DC regime as a very slow AC regime. I will do it in a quite brutal way. I will not add mutual inductances here because they are not needed. And I will put at the last column my DC regime. See what I'm doing? 1 millihertz. So do I have? Yeah, here is my DC regime for 3 nodes. And here goes set of AC, 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 some zeros, AC, AC, and C regimes. Let's go forward. Let's go forward, let's go forward, and what's forward? Interesting. If I put this again. No nonce, nothing fails. Okay. What's next? Now I need to perform a synthesis. I have DC regime, I have 70 AC regimes. Synthesis. Synthesis, voltage. Here is the synthesis with Fourier row. I create a Fourier row. Let's see. Should be 1 voltage. Something not. Because the it should work. I don't like what I'm seeing. So, wait, okay. Voltage is too simple. don't see. Where is my mistake? I don't see. It should draw up to 6 radians. And here I have only till 3.4. What's up? Double P. This is stupid. Oh yeah, oh yeah, oh yeah, oh yeah. Currents, voltages, look what I got. 3 voltage and 6 currents. I'll show. Currents, voltages. Wait 1 second, I will switch here, and here are my voltages. With the, you see how it's very simple code. I get my voltage via synthesis of Fourier rule. I don't know why my previous was only up to P. Actually, I have a omega P field with, where's my synthesis? Actually, I can use that not to calculate it. This one is not necessary. Actually, I can use, I'm wasting memory, I can use omega T values, but okay. Here is rectifier, here are voltages. What should we do now? Voltage in first, second, third, no. What should we do? Where are these voltages in the real? It's for very yellow line is at rectifier output. Looks looks like this. Now, let's go. Node 1 at capacitor. Yellow line, node 1. Should be 2 waves and up to 30 volts. Blue line is node 3. I will make it smaller. So, node 1 peaks are 24.
Maximum.
Not delta, F, 24.4. This number is cut.
Okay. 24.
24.4, 24.8, and here it chart. 1 second, I will. 26, something like this. Okay, next one, second node. Second is at 200 ohms. At 200 ohms here. Second node, 22.4. And a node 3, it should be here. Oh, scale. Here is node 3. Something familiar? Алло. Да, чем помочь можно? Where is my bar? Look at this voltage. Peak, down, up, and this is our calculate.
I will give the number. This ask. No.
Currents, voltages. Very smart. Тяжелый, кто сумеет тяжелый, когда на такой осмотр, то еще не у кого не глянул попробовать, не получить пользоваться. А у нас любители ни о чем. Пианисты играют любители. Видео, чтобы он эти. Я бы, может, и сам дернулся, но я вот эти по времени. Бог знает когда это. Такая картина. Непонятно. Так я на вскидку не увидел. Oh, you know what I did? I changed capacitance to 10 microfarads. What a nice sign. Let me check. The spike wasn't so ideal. Spike wasn't so ideal. 10 microfarads. Can I change to 10 microfarads? Then microfarads. Oh, look, what a nice voltages. 1 second, I'll switch to. Oh no. This is not a static. 1 second, I will rerun. 1 voltage, 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 and current, 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 current. You see voltage? First node, second and third should be with looks like an opposite. You see big difference? I see difference. And I move on. One, two, three, four. Do you see my voltage? Blue line is a voltage of node 3. And yellow is a voltage of node node 1. Looks close. And if I go for full rectifier, oh no, with the full rectifier, nothing to see here. Look how good works when I put put a full rectifier. Ideal. Wait a second. Wait a second. Full rectifier. For full rectifier, my filter is too good. Take a look how good it works if I use a full rectifier. Ideal DC component with very small AC. I need to make it work. You know what I'll do? I'll put 10 times smaller inductance in the branch 1. I will worsen inductance. Man, who have a 100 millihenries inductance should also have 10 times smaller. This one is 10 millihenries. What if I substitute 100 with a 10? Well, I have substituted my inductance and I will here where I need to change. Here will be, and it has an active resistance of 6.44 ohms. 6.44 here and 6.44 here. So I can do this one. Yeah, and let's see what will happen. Signal, voltages, currents, voltages, voltages. Voltages. Let's see what I have. Here is voltage at node 1. Top of it is a node 1 is at capacitor. Yeah, node 1 is at capacitor. Here is my voltage at capacitor. Only I see it mirrored. Why I? change the can we compare them? Don't know. Maybe oh no. This is one moment. I will here are voltages. Oh, can we compare? So can we compare what? What we should compare? We should compare this with yellow line. Looks similar. And this one from node 3 with the blue line. Blue line is node 3, yellow line node 1. Are they similar? They are. And what about currents? This is yellow line, this is blue line. Similar? Similar. Let's try to get currents. Currents. Currents, how can I get currents? Not everyone can get currents. ground attached. Let's see. It will be blue line. Current in the first branch. Current in the first branch. Blue line. Where are you? Here, first. Not in ideal quality. Blue line is a current in the first branch. Something familiar, isn't it? Yeah. Oh, no. It's not funny. Second. Here I will change to window number 3, and in here, one moment, I will make visible now online viewers can see both. So now yeah. And here. Result of this code. See this line? Is it similar to my blue line?
Yes.
Okay, let's take this branch 2. This one, it's a capacitor current. Should flow into capacitor. Compare this to this. Blue line with the branch current number 2. Similar?
Yeah.
Okay, branch current number 5. Branch current number 5, branch current number 5, for example. Or number 3. Should I take number 3?
3.
Number 3 falls into coil. I think it's this one.
No.
They're quite small. No. Disturbance.
Fluctuate.
And what about current flows in this one? Okay, I can take it here. It's my current number 6, but it's not a quite disturbed. It's above sensitivity of this clamp because it's designed for 20 amps. Maybe, I don't know. Try to bit high. It's on branch 5, but it's quite disturbed. Voltage similar, but okay, it's a reactive load. We know what the voltage is. I need a different. This clamp is too big. I can current of the. Here is current of the resistor. First one, 200 ohms. In a such scale, even my hands and I'm gonna attempt to switch to average. Falling to capacitor, you falling at capacitor. On. Capacitor's current, branch number 2. Capacitor current is strong enough. Which of them? This is. It falls this way. Yes, current into resistor. Looks like it works. What? Something like this. Yeah. So, technique is not so complicated. Decompose, calculate by 1, and compose. And it will happen. Yeah. Okay, appears it enough for today. Yeah? Too much of everything. It's not so much. Yeah. Now it's correct. Correct? Correct. Yeah, correct. So, now compare the number 2. I cannot. Ah. Compare the number 2 with the scope. This one with the blue one. Yes, it is. Voltage. Where are my voltages? Which voltage I'm showing? On where scope is connected? Scope is connected to capacitor. So its scope is showing voltage at the first node, yellow line. It's AC component. It's AC component. Okay. Plot of everything.